Hello everyone, welcome to this course and a continuation module on lithography optics. In today's class, we will see some of the techniques about resolution enhancement, and also we will see how the light traveling from your illumination source through all the condenser lenses and followed by mask and objective lens before it finally gets printed on your wafer. So, for today's thing, prior to, and we will also understand how mathematically it is modeled, right. So, I on the previous class I have informed that it is diffraction limited imaging. The entire kind of all beams coming throughout all this structure ultimately falling into the wafer, that is finally light is being calculated, or PR solubility will get changed because of a particular process known as diffraction based lithography or this interference. So, how do we mathematically approximate that? We will see that in today's class. Also, as I mentioned previously, that all the semiconductor industries mainly depends on the parameter known as resolution. So, how that resolution gets enhanced, or how you are getting smaller and smaller devices, right. If you remember, I informed about Moore's law, that how Moore's law is being maintained, or currently it is like more than Moore. We are in the era of more than Moore, where we have to think about something else. But for before that, prior that, how for 3 to 4 decades we can maintain that particular rate of miniaturization. All this thing we have discussed. Additionally, I have given a glimpse about the course, that what were the important topics have been covered or will be covered. Also, we have followed a top down approach to understand about what as the most, like how fabrication or micro machinings are important. Then we have seen in particular fabrication, what were the unit processes, which processes are important in fabrication. Also, we have seen that in that important process, what are the sub processes. So, for those who have kind of attended last class would be aware that fabrication has thin film deposition, lithography, and etching. These are some of the main techniques. There can be sub techniques into that, and like thin film deposition has PVD, CVD. In PVD you will get sputtering, E-beam, thermal evaporation. In CVD you have LPCED and some other variants as well. So, we have seen all this sub process and processing in glimpse, and throughout the course we have been discussing with this process and application with different process flow. Then we discussed that okay, lithography is important. In lithography, what are the important sub processes, or which is the most important sub process? Prior to knowing or identifying or assessing which is the known sub process, we should know what are the sub processes. So, we have seen that PR coating, photoresist coating, if required some form of wafer preparation, PR coating, pre-bake, exposure, post-exposure bake, and development followed by characterization. These were some of the sub processes. In that particular sub processes, which is most important thing that we have seen. Additionally, we have gone through multiple numericals. So, that I believe we have now developed an understanding how to, if spin speeds are given, how the thickness on the top of wafer of thickness of PR can be altered. We should know that if a particular pitch is provided for a given photolithography system, whether we can reproduce those pitch and numbers using that system or not. So, this kind of numericals I have covered. Not only numericals, I have also shown some of the additional information which is very useful. For example, we have seen that energy spectra, how G line, H line, I line, or even further excimer lasers like argon fluoride and krypton fluoride lasers have been used. What is the wavelength, in which particular range it lies, whether it is visible range or UV, or what kind of range it is. All this thing we have covered. Today we will definitely developed upon that, and we will see the mathematical modeling of optics and resolution enhancement techniques. another important point I have also shown about SU8 photoresist data and numbers, like every IC, right, comes with its own data sheet. Same way each and every PR comes with its own data sheet. So, I have shown you the number and encourage you to go through the entire data sheet of different photoresist, which I hope all of you have gone through. Okay. So, before we start today's class, we will see a quick recap of what we have seen before. So, this is our overall thing. The most important point or most important drawing is this one that we have seen this. This is a lithography process, and as I mentioned, condenser lens will be here, mask and objective lens. Let me just put a laser pointer so it will be easy for you. Yeah, so this would be your condenser lens, this would be your mask followed by objective lens. I mentioned earlier that condenser lens and objective lens is for the sake of simplicity. When I say condenser lens, it cannot be only one lens, there will be multiple lenses. Okay. Same goes for objective lens as well. Mask design, mask loader, all this thing. So, this was our fundamental diagram to simplified diagram to understand how lithography process works. Okay. Further, this was a quick question that which kind of exposure is this? Of course, as I mentioned, it depends on diffraction, also depends on the projection and all, and it is called projection printing. I have mentioned about reinventing the wheel, right. For any particular science, you should know how the flow is, how it has been reinvented from scratch. So, earlier it was contact printing, then I told you that if this is your mask and you want to print this on your wafer, you can do it for minimum number of time, then your mask gets deteriorated. When your mask gets deteriorated, you will not be able to get the same print, and as a result of that contact printing stopped. Then it comes to proximity printing, which has its own limitation of resolution of 4 micrometer, whereas I also request all of you to check what nanometer technology your particular smartphone uses, right. It would be in some nanometer. So, considering that this proximity printing's limit of 4 micrometer is not proper. So, then further we went a step ahead, or scientists have gone to one step ahead and made a projection printing out of it. Okay. So, that is also like an important one small point, but important point. Okay. Further, I have also explained about the resolution formula. I mentioned at that time it is an empirical formula which has been added after observations. That resolution depends on 3 things, right. One of them is system parameter, second one is wavelength, and third one is numerical aperture. Now, I have explained about if your light is getting incident in a normal manner, okay, this is your mask, this is your lights. If it is in normal manner, then means 90-degree angle ideally. Okay. If it is in normal manner, then the K value would be 0.5. If it is in oblique incidence, the K value would be 0.25. Okay. Based on that, your resolution would be calculated. That is what we have seen about the K value. Further, we have seen about the wavelength lambda. So, lower the wavelength, better it would be if we think about this formula as a mathematical formula. However, when you decrease the wavelength, I mentioned that these are EM waves, light propagates through your source, reaches the wafer. EM waves, they have their own relationship between the wavelength and the energy of a particular wave or beam. So, and also we have to consider medium, and also considering that we have to very cautiously lower the wavelength. So, that was another point. Also, numerical aperture is what we have discussed. Numerical aperture is an ability of a lens to acquire light. So, generally it comes into the consideration for objective lens. When your lights are getting diffracted at a higher and higher angle and gets deviated in the other side, that time we might not be able to capture the entire light there. As a result of that, we might get some of the diffracted light might get lost, and hence that is where numerical aperture comes into the picture. We have seen it quickly last time. So, we will discuss little bit more on that as well. Further, this is like a diagram. What I like about this is I mentioned that if you see here in the lithography sub process, starts from illumination, mask, exposure, objective lens, and finally the wafer. See, illumination, condenser lenses, mask, objective lenses and your exposure. Same way this is like this, okay, illumination, your condenser lens, mask, objective lens and wafer. It is like this form, flow wise top to bottom. You keep the same thing, rotate it by this and keep it like this. Okay. In that case, if you see, this is your source, condenser lens, mask, objective lens and wafer. Okay. So, same thing what we have seen, it is a simplified diagram for that. This is a diffraction limited imaging. Okay. I already mentioned that the entire overall imaging depends on your diffraction phenomena. Okay. Furthermore, we have seen what is depth of focus. So, I explained the ability of that light or ability of this particular lens, you can see here. Let me just, yeah. So, if you can see here, the ability of this objective lenses are placed strategically at a very precise location. So, how much tolerance you can allow for your objective lens or lenses, that is what your depth of focus. Now, the higher the value of depth of focus, it is better for you because you will get a chance to place it here and there little bit. Precise placement comes with its own challenges and cost. So, we have to consider all this parameter. I also mentioned that numerical aperture higher the better, but it will also affect the depth of focus. So, that is another point. We have to make a trade off out of it to design and get a proper resolution. We have seen that. Further, I have mentioned that if you just think about the formula mathematically, then what are the how can you improve the resolution. So, there are multiple techniques for that. I have briefly named it at the end of last class. These are the techniques and it affects the several parameters. Like as I mentioned, if you have a phase shifting mask, here generally you see what we have learnt is in the, if I can just 1 minute, I will put a laser pointer again. Yeah. So, if you can see it here, some of the lights goes through, other gets refracted and reach here. Generally, we do not consider a mask as a material that can change the phase of the light. Generally, we consider it can either get some diffraction, it allows some diffraction, or it will either, in a very simple term, okay, either it will block the light or it will allow the light. In a way, either it will completely absorb or completely stop the light, or it is allow. So, it will just affect the amplitude of the light. Okay. But however, if you use a certain materials, if it changes the phase also, it is called phase changing mask. So, there are some applications for that as well. We will see that. Off axis illumination, I have already mentioned that currently this is a normal incident, I told you, right. So, if you see here, this is a normally incident to your mask, this degree is 90 degree. So, if this is normal incidence, you have to, you will get some value of k, your system parameter. If there is something else, if there is some different form, like you will do some and that magic will happen from this beginning source, okay, keep it in some different position, you will get, instead of this, you will get this kind of thing. So, then whenever it collides with a certain angle, right, not 90 degree. So, that is called oblique illumination, and as a result of that you will get some different type of beams reaching to your wafer. It is a 2 beam imaging. I have discussed briefly about 3 beam and 2 beam imaging as well. Okay. So, that is another point. Further, we have also seen how resolution has improved over the years, right. So, I have taken, I believe, 2 instances and we have seen that how it has improved due to which particular parameter. So, this is just a summary of that, if you can see the screen. In 1975, this is particular values were there for system parameter, wavelength and numerical aperture, whereas in 2010 it has been improved to this portion. Now, because of which factor, how much it is improved, already discussed. Okay. One very last and important point I have given at the end of lecture, some scenario that consider this photolithography system is used. Okay, consider that this kind of illumination is being used, this particular wavelength and best possible numerical aperture. So, what was the limit for the lithography resolution for the given scenario? So, if you are watching this video, I would like to pause it, and if you have not calculated, please calculate it. Okay. So, that is like a overall quick recap of what we have seen. It is like an alap before any song, right, that will take you to the song. So, now Let us begin today's lecture. This is a Fraunhofer diffraction. Okay. So, there were two types of diffraction which we have studied in +2. One is Fresnel diffraction, other one is Fraunhofer diffraction. Now, what type of diffraction will be applicable in this scenario and why, you should know. Okay. Let us see that. So, this is diffraction, as you already know, bending of a light at pass through the slits or edge. Okay. Whenever there is enough gap is there, it will easily pass through, but when there is a slit here means there is some change or some kind of form of edge or some slope or something like that in your mask, right. When there is an inconsistency or some shape in your mask, it will get diffracted, and that is exactly what we want, that your desired design or your mask design should get reflected in wafer. So, that is what possible with your bending of light, but only one lens is not enough, because it will bend the light or diffract the light. Okay. Then what? You have to collect that light also. So, there should be a complementary lens placed, and that is when the pair of condenser lenses and objective lenses comes into the picture. Okay. So, this is like your diffraction definition, okay, considering boundary condition. This is a flow which we already seen. So, there are two types of diffraction, as I mentioned. One is Fresnel diffraction, other one is Fraunhofer diffraction. So, in this case, what kind of diffraction would be applicable? Before seeing that, I will just explain. This X is hidden here, okay, in this space width here. Okay. This is your X, whereas this is your distance between your mask and objective lens. Okay. So, now you see the overall formula or kind of a criteria to decide which particular diffraction method is possible in this case. One is when your X is the distance, this is by the way, this is called a space width. So, if I can just quickly anyways we will be discussing in greater detail in future, but I am just drawing this line here, okay, and let us say this is your design in your mask. Okay. We will see this in detail in this class only. Then there is some space, again there is some design, and again there is some design. Now, it is almost, consider this is an equal thing. Okay. So, this particular thing where your design is there is called line width. Okay. This is your line width, whereas this thing, okay, which is there where there is a gap, right. So, that is known as space width. If you are discussing anything related to lithography or this kind of imaging, these are very known terminology, line width and space width. And finally, if I take from this line, let us say it is getting here and this is getting stopped here. Okay. So, this distance whatever you are seeing here, okay, is nothing but your pitch. Okay. So, what you are getting using Rayleigh resolution formula is half of this, half pitch. Okay. So, this is terminology. Why I explained all this thing here is, let us consider, if I say now that let us consider X as your space width, then all of you should now understand that what do I mean by space width. Again, line, when the line is there, space where nothing is there, and summation of that is your pitch. Okay. So, let me just erase it. So, that is your line width and space width. In this scenario, your space width is X, whereas the distance between lens and mask is small d. So, again I want you, all of you, to stop the video and check which particular criteria is applicable here. Okay. So, yeah, which particular criteria is applicable here in this case. So, the thing is, if you have seen this is a micro nano fabrication what we are talking about. So, your device dimension will be in micro or nanometer range. Additionally, I hope or like some of you have at least searched or googled about the photolithography system. If you do that, if not please do, if you do that, you will get an idea that photolithography system is almost of the height of a human being or even more than that, and they will put it in a such a way that in front of you there will be a screen, okay, where you, GUI, where you can operate and identify and tune the parameters. So, considering that your distance between your mask and objective lens would be at least few hundred of centimeter, in contrast to this particular design which is there on your mask, which is like a small axe which is in micro and nanometer range. Hence, this Fraunhofer diffractions criteria will get specified or will get satisfied. In that case, we have to apply Fraunhofer diffraction, and then Fraunhofer diffraction has its own rules, and Fraunhofer optics will comes into the picture. So, what is that? Basically, see, main thing is our agenda is to identify that how this diffracted light goes and how we can quantify it or model it here after it leaves the mask. Okay. So, this is the formula for Fraunhofer diffraction, that electric field of diffraction pattern is Fourier transform of mass transmittance function. Another very important point here, as I mentioned, this light is electromagnetic wave. So, if you want to model it, you can easily consider your electrical field and then you will get a magnetic field which will be a perpendicular to that, right. So, this is the basic point of that. So, see the formula, electric field of diffracted pattern is Fourier transform of mass transmittance function. Now, why electric field is important? Because electric field will give you ultimately the intensity. Now, another point, ultimately what we want, that whatever is there in mask should get reflected on the wafer. So, based on the design on the mask, what we are getting on the wafer, it should have a two different solubility, and that solubility can be changed by calculating the intensity of the light, and that intensity can be calculated by considering the electric field, which is what we are checking it here. So, electric field can be calculated by the Fourier transform of mass transmittance function. Now, Fourier transform, generally what we have studied so far is a function that can change one domain into another domain. Majorly when we are dealing with time domain signal, we convert the Fourier your signal, time domain signal, into frequency domain, and there are some properties of Fourier transform which all of you should know, like what is duality property. The time limited signal will have a infinite frequency components. If I talk about band limited signal, which will have a finite time domain, infinite time domain. That simply, if you consider one sine wave of one frequency only, it has only one component in frequency domain, but when you plot it into time domain, it is expanded or it is extended towards the both sides towards infinity. On the other case, if you are talking about any small square wave or something, when you draw a frequency response of that, you will get a sinc function. Sinc function is again, as I mentioned, extended for both sides in frequency domain. Okay. So, these are like basic things or fundamentals about Fourier transform which you should know. Coming back to lithography, this is your electric field of diffraction pattern is Fourier transform of your mass transmittance function. I want you to analyze both the equation. Let us say this is your equation number 1, okay, and this is your equation number 2. Okay. Analyze both the equation and see what are the similarities, what are the differences. Again, as I mentioned, for resolution, when we thought how we can improve, we just thought mathematically. Just think about this from a mathematical perspective, and what do you observe? Okay. So, here are the observations, that this is easy one. First of all, this is easy one, okay, which is like a single integral, some signal is there f of t, and then you are getting your transform f of omega. It can be omega, it can be f, like angular frequency or linear frequency. So, this is your frequency, this is easy one to understand. So, I started with that, and it is single time integration. So, whereas in this case there are double integration, limits remains almost same. Now, we easily understand, like okay, there is a time domain signal, we know what is happening, okay, there is some time domain signal. In this case, what is Tm? That should be the first question. Okay. So, what is Tm? And also in frequency domain or in the simple Fourier transform formula, there was f, which is your frequency. Now, what is fx and fy? Okay. So, those are your scale coordinate or spatial frequency. It is defined with a particular settings. So, before we see how they are scaled coordinates and how it is calculated, let me just erase this. Yeah. So, you see this particular thing, this is your mask, this is your mask which is shown in black. Prior to that, this is a loader, okay, it gets diffracted by a certain angular theta. For those particular case where it gets diffracted, you will get this kind of value. Now x prime is here, z is here, z is the distance between your lens and mask, whereas x prime is nothing but your how much it is elevated towards the upside. Now y dash is here but not shown here because it is inside the screen, okay, it is a 3 dimensional phenomena. And this is just to brush up the basics, that what do you mean by destructive or constructive interference. This entire game depends on this how much optical path difference is there in terms of your lambda. So, if it is like n lambda or with full cycle, you will get a very nice constructive interference, you will get a bright spot there. Bright spot means most of the beams are getting localized, that you will get a good energy there, okay. Whereas if there is a like destructive interference, you will get a dark spot, okay, and you will not get any form of light reaching to that particular point, okay. So, let us quickly take couple of examples to have an idea. So, this is your mass transmittance function, okay. I explained, I like you briefly talk about mass transmittance function. It is very easy, just see here, here the light, okay, is coming from here, it is a small let us say one from here, one from here, okay, and it is getting blocked. Now depend on your mask, either it will get blocked or it will get passed through. Consider that black region currently is blocking your light. So here there is no light coming out from this portion. How much light is coming? There is no light coming, 0 light. Same as here also, 0 light passing through. Whereas in this case you will get all the lights passing through, right. So this is mapped, mass transmittance function is the mapped quantification of how much light can pass through the mask. So you see, as I mentioned, there is no light can pass through here, so you will get all values 0, same goes for here as well. Whereas here full light is getting passed through, so you will get 1. So this is an example. I hope now it is clear what mass transmittance function is, okay. Once you have a value of mass transmittance function, you just have to put it into this integral and calculate what kind of diffraction pattern you will have and plot it. So you will get an idea, okay. Let us see that. So this is your mass transmittance function, you know the value, right. Everywhere else it is 0. Another important point, here we have mentioned W, okay. Now what is W? Line width or space width? Pause it, think is and tell, it is a space width, okay. So this W, so we need your final pattern in terms of value of W. So let us calculate it. Again, this is a mathematical derivation, it is nothing but a normal integral, okay. So it sound again, it is for the sake of simplicity, we are showing it for one dimension, okay, just to get an idea. Further you have to kind of superimpose several dimensions thing and also calculate. Just put a value 1 here. Now this width is W, which is your space width, right. So take it, make a system or shift the origin or understand it from here. This is your 0, so this can be your minus W by 2 and this can be your W by 2. So with that limit you apply the value, put the value and calculate the integral, you will get this kind of diffracted pattern. So this pattern is coming out of the mask, that is again a sinc function, right. So I mentioned time domain square wave or one pulse frequency domain sinc function and vice versa. So you will get this kind of sinc function, but how it will look like, right, how finally the value or finally the diffracted pattern will look like considering this as your mask. So it will be something like this. Again, ideally sinc function is extended both sides towards infinity, but not everything we will capture because your objective lens has a finite duration, I will come to that. But this is clear, it is very simple, right. Here we have taken only one instance where 2 line width and 1 space width is there. Let us see one more quickly, one example. Here we are having a repeated line width and space width. So in this, if you calculate the value and put it, you will get this kind of thing. Do not get overwhelmed by the formula, one by one we will see. First we will take this case of diffracted pattern. You see it is written repeated line and space, okay, whereas here it is written equal line and space. It seems like it is equal line and space. If we what we have seen previously, this is your line width, okay, and this is your space width, it almost look equal. This is your W, let us say this is line width, we will just name it L, we will not be using it though, and this is your P, Now when equal line width and space width are there, your W, which is your space width by P, will become 1 by 2, which is nothing but line width plus space width. When it is equal, it will be like this. So this is your overall formula. I will share the link of this, how it is derived. Okay, will not go too much into detail for the in the mathematical derivation, but this is how it has been calculated. Now if there is a equal line width and space width in both the cases, you see this W by 2 will get replaced by pi by 2. W by 2 will get changed by P by 1 by 2. Okay. Just put a value W by P 1 by 2, n pi remains as it is. Okay. So this is again a derivation. Now the important point is here. Here you are seeing a sinc function, okay, when there is only one space width. In this case you are getting a result from multiple beams, because you see there will be, if I draw a little bit more, light coming from here, okay, might get diffracted here and reach to this point. Same goes from here also, sometimes it get diffracted and reach this point. So all these sinc functions, there will be repeated sinc functions, will nullify its secondary and side lobes, and you will get this kind of impulses. So this would be your diffracted pattern. Again it is important to see that you will get diffracted pattern here also, here also. How many numbers of this impulses will pass through the lens decided by your objective lens. So how do we calculate that? We will come to that, depends on aerial imaging. So you can find the solution here of the previous derivation. This is an important point, that numerical aperture of the objective lens allows finite diffraction order to pass through the lens. You see here it gets diffracted, not everything, every light or every order gets passed through. So it will get decided by how many orders will get passed through the lens, eventually forming an image on photoresist. It is clear. Whatever orders have actually reached to objective lens, that only plays a role in deciding that how my final image would be look like, and hence always whatever you have decided on your mask will not completely get reflected and you will get a shape here. The objective lens is described by pupil function. Another important property, very important property when it comes to lens, is your pupil function. Pupil function will decide that how much light you can pass through, right, which is a function of spatial coordinates and describes numerical aperture. Already I have discussed fundamentally or conceptually what is numerical aperture. Pupil function is a derivation of that particular thing. Okay. Given the mass transmittance function, there should be a small tm, okay, and then you will get a diffracted light, which is your, see I will tell you easily, this is your mass transmittance function, then it will get diffracted, you will get this, then whatever pass through and reach here will reach here. Okay. This is mathematical like quantification or modeling of that. If you have a mass transmission function Tm, pupils function P, then how much light will go through this? After let us say this is your mass transmittance function, okay, this is your diffracted light, and this is your final lights coming out of objective lens, or light reaching, you see that, okay, light gets reaching to objective lens, okay, and further it gets diffracted and then we can model it. So this is for this particular point, this is for this diffracted thing here, and this is here, okay, easy. So the thing is, when you given this particular thing, how much diffracted light will reach to your objective lens gets decided by P into Tm. P is just simply, if I say it is an enable pin or something, like this based on the dimension, this much light will pass through. So this is getting decided by P, and what light is coming, input light or diffracted light, is capital T into M. So this is light, this is what the lights what we are getting here, and further this says that objective lens performs imaging in the form of electric field, and it can be calculated. See, I already told that how mask or lights get diffracted can be explained in the form of Fourier transform. But then another property, how it is getting diffracted, but when you put a lens, you can calculate the final light by taking inverse Fourier transform, in a way completing the cycle. Here it is f, okay, your Fourier transform, whereas here you can say that Fourier inverse. So ultimately mathematically also, whatever you had here in mask, you should get it here with some changes, that is depend on your numerical aperture or pupil function. So, now if you see this formula you should be able to understand that I explained here how much light is reaching to your objective lens P into Tm. Now, property is there for objective lens that it will make the outcoming or output light from objective lens is inverse Fourier transform, it is modeled like that. So, that is your electric field, this is your electric field, okay, and you square it up you will get a intensity. So, this is basis of how it is reaching. Again, once you see this much intensity will reach here, there are further analysis, you have to find out bright dark spots and bright spots intensity shown or known as Imax and I mean. Considering that there is something called contrast is defined, that how your setting is treating your overall lights or both the lights differently when mask line width is there and not there, okay. So, that is again an important point. So, now we will see as I mentioned this is a like cross section of objective lens. You can see the objective lens here, just a cross section of that, it is showing that out of this many orders, okay, you have 0th order, first order both sides, third order. Now, second order is not given because let us say in the destructive interference it has been vanished. How it is happened? You can check in this particular link to identify that why this particular order is not present, okay. But the lens is saying okay, I am that much big only that I can only cover till this point and this point. So, then you see that you are taking 3 beams into consideration, hence it is called 3 beam imaging, okay, important point. And here you see that light is incidented normally. So, in this case it is like that. Let us say if you change your light source, this spectra will get shifted by this side or this side, as a result you will get only instead of 3 beam 2 beam, again an important point of consideration, okay. So, we will see that in the near future. So, now we will see quickly we will see the 4 resolution enhancement techniques, which is an important process to get your desired resolution, okay. First one of which is your immersion lithography, very important. So far now you see immersion means some fluid, okay. So, mathematically also if we think that immersion lithography value is more than like 1.3 1 kind of how can you increase your numerical aperture? In optics if you know numerical aperture is nothing but your n sin theta, right, where n is your refractive index. What if we can increase the refractive index? If you increase the refractive index you will get a higher value of Na. Now, you put a higher value of Na you will get a lower value of resolution. So, that is your resolution enhancement. And how do we do that? By changing the medium. So, very simple, you see this is your lens and this is your wafer on which resist is stacked, okay. This lens when I say I am talking about objective lens, in between so far whenever we have not mentioned it is air, okay. But what if we change the medium from air to some fluid? As a result of that you see this n lens numerical lens refractive index is 1.5, whereas here you see it is 1.44, okay. Here there are 2 examples also provided, that instead of a dry focal plane which is coming much earlier you can extend it to a further dimension, which will help ultimately in deciding where your wafer should be and what should be the distance, and there are much more consideration. So, that is your when you are dry exposure and wet exposure you will get a different image, and it is known that with wet exposure you are getting better image, okay. So, that is very good, right, we can improve the resolution, but and again there is an 4 cases given at 2 different wavelengths, and it is known that for the same numerical aperture immersion has a better depth of focus, giving us more provision to placement of the objective lens. Each and every good thing comes with its own challenges, okay. So, then what were the challenges when we are using immersion lithography, okay. Again this one side point is this depth of focus. When you are using immersion lithography the same formula of depth of focus will not hold, there is some slight change in that, which is good because as I mentioned for immersion we are getting better depth of focus. This we have already seen, I have explained it while doing this particular thing, so that is cleared. And what are the challenges with that? So, first and foremost, we are using fluid instead of air while we are scanning or exposing. So, the important point in this case is, you see this are like you have to put the medium into that, and even a smallest of bubble. Okay, last time I mentioned that if there is a slightest change in design or mask or process, it will get hampered, your device, all the device will get hampered and you will not get a desired pattern. I was referring to this as well. If you have bubbles, a small bubble, okay, can result in a defect in mask and you might have to recall the entire device. So, it is very cautiously should be taken care. Also you see here there is a water and here there is a PR. Now PR is a chemical with finite viscosity and properties. So, that should not get changed, PR's own property should not be changed. So, there is something called guard or some, to guard the PR, there is one top mechanism is being used, I will come to that. So, then water interaction with PR you need to take care. Okay. Hydrodynamics delay, this when you pour water at a certain flow with precisely you are pouring without any bubble and defect also, when you expose it, this exposure light is of a great energy, it can heat the water and then light travelling through might not reach to the exact next time, or when you perform multiple runs it might not be possible. Hence you have to cool down your water in, hold there and wait for some time, or remove the water and put a new water. Okay. So, this all are like important drawbacks or challenges when you use immersion lithography. However, people are using it just to give you an overall small illustration. I have added this shots. So, just please see this, you will get an idea how nicely or better you will able to see things with lithography. This is a dry lithography. Now, when you use immersion, okay, you see the change. I will play it again just to give you people an idea. This is a dry lithography, you are not getting a proper focus, you see here. Okay. Whereas, when you use immersion lithography, you are getting all beams converging to a one particular point. Again, it depends on your scenario, but just a good illustration. So, I thought of including it. Another very important point, resolution is not only about making things smaller, it is about getting the things more accurately as well. So, if somebody says that okay, you are getting earlier 20 nanometer, now answer 20 nanometer, what new things you are adding upon, that can be multiple things. Okay. So, that is like a very good takeaway, that if you are getting a better image also, that is good thing. Okay. Ability to pattern smaller features on the top layer of the substrate, ability to pattern small side feature. Now, this again, now we have already seen this, I will not come to this, but the thing is immersion provides accurate features with better focus. See, this is the important trivia that 1984 it has been started. Okay. Well, IBM confirmed that lithography can be done in, or we are doing it in 2004. See, 20 years they have checked and seen through that whether it is good enough to go ahead or not. I was mentioning that cost factor is very important, and whatever you are getting, okay, they have to cross check everything before proceeding with photolithography, otherwise financially also a big loss, and not every semiconductor giant can afford it. Okay. Also I mentioned about top coat, right, top layer should be properly isolated from water, so there should not be any form of diffusion between your PR and the liquid medium. And just to give you an idea that cost, okay, to do one particular run, right, one experimentation exploration, it is 30 million USD, only 248 crore rupees to do this particular immersion lithography. Okay. These are I think slightly 1 or 2 years older numbers, but you can have 250 crore rupees, then you can explore this particular thing. Okay. And that is why they will take utmost care that the process will not fail and you will get a desired product. Immersion lithography is most widely used with highly purified water, I already mentioned. Anything which is less than 45 nanometer, okay, uses, or sub 20 nanometer uses this kind of lithography. Now we have been trying since 70s, 80s and all. Another fun fact is that oil immersion is being used for almost a century. Sometimes the things which is happening in front of you or seems very easy, you might not find out. So, it obvious. So, that is like a fact that immersion was already used for microscopes and all, but we are reluctant to use it for this. Now it is being used, we are getting good results. So, that is one of the RET. Second one is optical proximity correction. So, this is another important point which I like to explain. You see, focus on this particular image, you see there are two instances, one is without optical proximity correction and one is with optical proximity correction. These all are reasons why we are not getting proper image which is there in mask. Same thing cannot be obtained here. There are reasons for that which I already explained. There might be a non-linear response, contrast might be difference, you are not getting proper interference and all this thing. Not go into too much detail, but you see these are the two examples, one is this, other one is this. Okay. So, you see here that one is without optical proximity correction, this was your input mask, this is what you could get on your wafer, whereas this is with your proximity correction, this was your input mask and you got here. All this aberration will slightly alter your design. So, if you already know that this kind of alteration happens, how can you backtrack it and get a better design on your wafer. So, this is overall idea, it is like a closed loop non-feedback non-linear feedback control system. Okay. You do this thing and evaluate the algorithm, if it is satisfied, great, your mask design is done. So, this and all is like a prior step before loading mask, and you have to add some additional features called SRAPs, sub resolution assist features, which is not actually a part of your design, but you have to use it and that will help in get the desired design. How do we do that? I will show, but prior to moving that, fabrication process below 250 nanometer uses OPC, optical proximity. There is something called process proximity correction as well, we will come to that. But the examples of this, see why I have taken this example is, you see this is without OPC, this is with OPC, okay, and you are getting desired pattern below which is shown, but the blue one you are having several things including line and shortening. You see you are not getting a proper ending at both the sides compared to the green one what you can see here. Okay. Why do they get this particular thing is because of this kind of serifs or SRAFs added, sub resolution assistive features. Okay. Very important thing, and you have to add. How do we come to know that we have to add it here? You see, this is not only about adding, from this thing it has been edged also. Okay. So, there are known data, and you know now with the advantage of machine learning and all, known shapes using which you can identify that which kind of pattern finally will get generated on the wafer. Okay. So, here you see 180 nanometer technology, which has been a very prominent technology node in terms of VLSI, and there are two things, one is rule based and one is model based. Rule based simply works on lookup table thing, whereas model based work on the calibrated model. There are different shapes instantiated, so you can use that and get your final thing. Okay. There are drawbacks as well. This mask writing is more computational. Okay. You see this mask, okay, mask number 1, mask number 2, which is more complex, of course number 2, but gives its own fruitful results. Okay. So, mask writing is computational. If it is more computational, time will also increase, and the most important and the biggest challenge is your mask inspection is more difficult. Let us say you are not getting a desired pattern, you have to backtrack to your mask, then what went wrong or which shape has a problem. This is simpler to understand and analyze. Okay. This is complex, but with that we are getting good resolution or accurate resolution. Okay. So, this is another point, another OPC. We will see the third OPC which I already covered, so I will not go into the detail of that. Off axis illumination, just quickly, this is 3 beam imaging versus 2 beam imaging. This is the case of 3 beam, right, because you see that beam number 1, beam number 2, beam number 3, okay, is passing through because of this normal incidence. Okay. Whereas, if I talk about this case, here you see beam number 1 and 2 is only passing, where third is due to the finite range of that is not getting passed through. So, this is 2 beam imaging. How, when it is possible, you see this is normal incidence, this is oblique incidence. Okay. You see here along axis or normal incidence, and off axis or oblique incidence. Okay. And also there is methods to illuminate a particular source. So, that also we can consider, that whether it is conventional like this or it can be annular and all, you can explain, you can kind of swim by yourself and check which particular formation gives you better image. Okay. And this I already explained that each point on the source generates an image on wafer. Final thing can be calculated with superposition theorem, but nowadays before calculating there are simulators available from MathWorks and Synopsys and also available in the GitHub as well. I would strongly encourage you to check all these softwares and know how the final point or final image on the wafer is being calculated. Okay. Finally, the phase shifting mask. Okay. So, this is your phase shifting mask. There are 4 cases. I mentioned that sometimes you see this thing, it is blocking the light, right. So, generally the chrome glasses which has been used for mask is only modulating the amplitude of the light and not the phase. But if we use some particular material that will help in changing the phase of the mask, and as a result of that by adjusting the thickness of quartz you will get any phase difference. When you get any phase difference you can check what and all image you are getting on your wafer. Okay. So, this is your overall 4 cases will be given. We will see all cases one by one. So, you see that case number 1. Case number 1 is nothing but binary mask. Okay. This is your mass transmittance function, red one is your mass transmittance function, this one is your diffracted or light, diffracted electric field, and this is intensity. Okay. So, you see here this is simple mask what we have been seeing, this is 1, this is 0, 0 1 0 1 0, simple. You are getting this kind of diffracted pattern where as I mentioned side lobes gets eaten by each other and you will get this kind of intensity. Okay. And with this intensity when you reach to a wafer your PR will get affected like this and you will get this profile. See what was your profile or what do you want in mask compared to what you get here. Okay. Let us see the second example now. Second example, you are using an inverted mask or phase shifting mask by 180 degree. So, you see when light is passing through 1, when it is not passing through 0, when your quartz is there it is inverting. So, you are getting 1 0 minus 1, again 0 1 0 minus 1 like that. As a result you are getting this kind of pattern, and when this pattern is there, when you square it up to calculate the intensity you will get this intensity pattern. When it reaches to your wafer, instead of what you are getting here, okay, nothing was here, right, you are not getting any features which you want, now you are able to get the features here. So, that is where your resolution enhancement happened. This is another case. If you take third case, it is half tone mask, okay, or H quartz mask or Levinson mask, that is your third mask. So, you are getting, see here it is etched itself, that mask only itself is etched. In this case you are getting, let us say 1/2, 0 and minus 1/2 like that. Okay. So, there you are getting this kind of electric field resulting in this intensity and you are getting this kind of feature which is more closer to what you want. And finally, if you are using half tone mask it is 1/2 and 0 or something like that. So, based on the thickness of this thing you can tune the mass transmittance function, that is where everything begins, and then you can calculate your intensity to get an idea that how solubility of PR will change. This is of course after development, okay, after exposure you have to follow all the post exposure bake and development and all the steps. So, there are some more further techniques which is kind of considering time constraint, I will not go into the detail, but I strongly encourage you to check that, that is double patterning and triple patterning, nothing but you are doing the same patterning things twice by shifting a mask or using 2 complementary masks and 3 complementary masks. In a nutshell, if you have a 60 nanometer design, if you use double patterning, you are getting earlier 60 nanometer pitch, if you use double patterning you will be getting around 30 nanometer, or if you use triple patterning you will be getting even your resolution gets halved. That is why it is known as LELE, litho H or litho H. Now, we can further go and get as smaller as possible, right, sounds very good, but when you are using multiple times lithography and etching it comes with its own cost and complexity. Okay. Hence, people limits to repeating this thing in one exposure only if we are getting, that is affordable and better, and that is where all the magic what I have quickly discussed in this phase shifting mask or off-axis illumination or optical proximity correction or immersion lithography comes into the picture. Okay. Just to give you an overall idea, you see this thing, this is your growth in terms of VLSI industries, Last time I mentioned that okay, resolution gives you 50 nanometer, how can we reach from 50 nanometer to 2-3 nanometers. So, agenda of my today's PH session was to make you people realize that oh yeah, if we do that we can reach to this particular point. You when you go from here to here, when you go from 20 to 5 nanometer or getting device dimension as smaller as possible, you have to add more and more magics here. Okay. Here it is not mentioned, but all this thing uses immersion. All this thing uses proximity correction, optical projection. All this use oblique illumination. Okay. Along with that, there are some self-assist double patterning, or that is a double patterning. You see 2 different colors in mask, whereas in triple patterning 3 different color, quad patterning 4 different color. Based on your budget, based on your process flow, based on your system, you can explain or implement any of this. Okay. So, these are like 4 techniques which I wanted to discuss quickly and make you people realize how can we reach from 50. First lecture I try to explain how can we reach till 50-60 nanometer. In this class I try to explain how can we reach from 50 nanometer to 2 to 5 nanometer. Okay. But still, as I mentioned, people are still going ahead and making device with 2 nanometer, 1.5 nanometer, how it is possible. So, if time permits we will see that. Otherwise, there is something called EUV and all I would like to discuss. I would like to encourage you to check extreme UV lithography and all this thing, E-beam lithography and all, combinations of several resolution enhancement techniques comes together to get your final device. Okay. So, that is it I have for this lecture. If you have any questions or something, feel free to connect with me, email me, would be very happy to answer that questions. Go through this thing, very important, both the lectures, and try to understand how we can get the desired pattern from your mask to wafer with desired resolution. Okay, fine. That is it I have for now. Please take care.